I'm Mar Gonzalez Franco from Microsoft Research, and I will be presenting measuring system visual latency through cognitive latency on video see-through AR devices. Measuring latency is a very complex process, and as systems get more components, it is harder to grasp the real latency, and that's introduced by each different component or modification. First, I want to go a bit on the background and different techniques that have been used for measuring latency. Many of them have been based on this idea of constrained motions, like a pendulum. Created in the 90s. This technique uses a pendulum, attaches a sensor to the pendulum, and then has an external camera that sees both the pendulum and the output of the display. That shows what the sensor is measuring. And this way you can sort of frame count how many frames are there since the pendulum went through the center until you saw that in the screen. There have been instrumentalizations of this and have created these great approaches of this using photodiode LEDs that detect when the pendulum crosses, both on the display side and on the pendulum side. So it's easier to compare both. Newer techniques have facilitated the use on a bit more on the wild, in which you don't need a constrained motion to measure the latency, and they use phase differences on a grayscale between the grayscale you're seeing in the real screen and the grayscale tracked motion you're seeing on the virtual screen. There are more details about this in the paper by Max Di Luca in 2010. More recently, with the arrival of high-speed cameras, we've been able to have an observer camera technique, which is seeing both the sensor input and the automated input on the outside, and that can have a very good way of near continuous latency reporting. But it doesn't really matter which technique you use. The challenges are very similar across the techniques. Different methods return different results. The latency can vary over time because of varying frame rates, or maybe the user looks in a different direction and it has a different rendering load. There is a need to sample over multiple events also. And it's hard to evaluate the latency without hardware, instrumentalizing photodiodes. It seems quite complex. Also, as you add more components, the latency will be accentuated, and some components are not synchronized, so it's hard to evaluate. So we're proposing a new method. The new method is they use the human as the measuring machine. And every VR system has a human. So in theory, if you're able to measure the performance of the human inside the VR environment, you could see whether their performance is showing any latency. For example, what I try to say here. Humans respond to outside stimuli on very specific range of milliseconds. For example, visual stimuli are integrated at a neuronal level about 200 milliseconds. The auditory signals are a bit faster, around 100 milliseconds. And there are additional delays in cognition that are added by the response. So if you're asking for people to see something and perform a task, then it will be closer to 300 milliseconds, which is similar to the Ericsson flanker response task, in which people are asked to move in one direction and they move. There is more detail about these different cognitive latencies in our paper. And these numbers might vary a little bit between people, but they are very stable within a person. Like if I take 200 milliseconds to perform on a visual stimuli, that is more or less what my performance. We prepare an experiment to test this idea of cognitive latency as a way to measure system latencies. And we want to also explore how multiple consumer devices are doing, particularly on the aspect of video see-through performance. Like if you want to see through the world, we're interested for multiple reasons on VR on the Wild at Microsoft Research. And we even have our own prototype of see-through device, which is the Prism, which we compare to these other devices that people already know. If you want to learn more about the Prism, there is a website there. So we set up a motor task in which people have to raise their hand from a button whenever the button in the screen changes color. And let's play the video so you can see how it works. It changes colors. They have to raise their hand whenever it's black. And they go through all the different video see-throughs with this test, all the devices and also without HMD. And we measure how long did they take to lift the hand. So of course, we need to compare this to a control measurement that is more similar to the approaches I shown before. And we use this modified outside viewer technique of high-speed cameras. So to do that, we also have created a millisecond accuracy clock. And what we do is we have a camera that looks directly at the clock and a camera that looks at the clock through the VR system. And then the cameras are synchronized through another Arduino, and we capture a frame every 5.5 seconds. We have that going for 30 minutes. With each device, we capture approximately 325 measurements. Of course, only a subset are legible because we synchronize the cameras, but the cameras are maybe not synchronized with the display of the HMD disparity. So sometimes we just catch the black frame of the HMD. And here are the details of the shutter speed, and it's using manual focus. The scene is also very well illuminated. Here more details about the clock that we have created, and also we have open source the code, and you can create your own clock if you want on Arduino board Duo. And basically, I want to show you a very high-speed video of how it looks. Generally, when you're just bare eye looking at it, it only looks like 8888 because it's a microsecond actually accuracy. So, and now it slows down, and you can see the super slow motion video that we created. You can actually see how it's rolling, and in theory, yeah, now it goes back to super speed. At the beginning, you can see also how it's super fast, right? Okay, and let's go. So one thing we need to do is synchronization of the cameras and verify that we have synchronized the cameras correctly to capture at the same time. So we set up this other small setup in which both cameras look directly into the clock without the HMDs in front of them. And we see that both are capturing the exact same number. That means that they are synchronized. So once we have that, we put the HMDs in front of one of the cameras. These are the results. So on the cognitive latency side, let me see if I can highlight things here. Yeah, so on the cognitive latency side, we have the baseline, which is how fast people were with the PC only, releasing the button. And this is between 300 and 350 milliseconds that, if you remember, that is kind of, here it is the exact response time. That is kind of what the literature shows on motor tasks, rapid motor tasks like the RxM flanker. So that is a good validation. And then we have the response that people have on the different HMDs, right? What we can do is we can take the baseline out of the different devices, and then we end up with because the baseline is how long does the motor system work for a person, how long does it take to respond, and then that could be the baseline for the other ones. You can normalize and find out the exact latency that, or infer the latency of the system, right? And here we can see this inferred latency is basically each of the devices minus the baseline. So here we can see the inferred latency using the cognitive latency. And we also have the measured latency that we measure with our clock and the observer approach. So, few things. Here we see all the latencies across the different devices and methods. Details on the significance of these are on the paper. I have to say that the index is giving a bit higher latency because of how, in Quest and Drift, the camera goes directly into the screen of the HMD without going through the computer. In the index, what we did is we retrieved the images from inside Unity and then re-render them in Unity, which of course is going to take longer. That same technique was used with the Prism, but the Prism is a device that was designed to do that. And you can get more details, as I said, on the Project Prism in the Microsoft Research website. So a few things that we find from the infer, the cognitive latency versus the measure photon to photon latency. First, we don't find significant differences between the methods. So whatever we found on inferred was comparable to whatever we found on measured. And you can already see that here. There is a larger variability on the variance for the infer method that may go away as we increase with more participants, because different participants will have different latencies themselves and in the performance of a task, and over a larger data of participants, I think that would converge into closer to the measure data. And then regarding of the latency, we were able to rank them, and the Prism was the top performance. Then we had the Quest, the Reef, and the Index. So those are the results, which I think are also interesting in terms of knowing which devices are the best performers. I think this new method of cognitive latency contributes to the general challenges of measuring latency. I think, first of all, there could be maybe a standardized task that we could find that will help compare the different methods up to now and how they compare to this cognitive task. Maybe attaching the sensor to the pendulum and then showing whatever the sensor shows in VR, and that's the trigger for the motor task, or maybe something else. Another good thing about this method is that we can measure over time in a continuous way how people are performing to a task. Maybe something like Beat Saber, you can see whether people are, the latencies are changing over time. And you can do it in a very large way because you don't require new hardware to instrumentalize every single device. You just require a human, and every VR system already has a human. And it might be easier to check which components create latency because you know what the person is doing at the same time as the latency is being retrieved. So you could figure out better ways to figure out the different components that are introducing latency. Finally, a conclusion slide. Very simple. It's an easy method without the additional hardware. It can scale to crowdsource, and it can measure online latency. Is it increasing or decreasing over time in this particular task or system? And one of the things that we believe is that there are more possible tasks to be used for other types of devices that are not video see-through. Like I mentioned, the instrumented pendulum can have a counterpart VR task that you need to perform, and it doesn't need to be properly a video see-through. And with that, we can go into the questions. Thank you.